Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we're in AP Chemistry, talking about thermochemistry. I got some fan mail. I have like 1.2 thousand subscribers, and I've started getting fan emails. It's kind of funny. All right, I don't make any money at this though, and I don't think I ever will, but that's all right. It's for you guys if you're out, and for the homeschool community, they use it as a resource. My niece lives in Texas, and she asked somebody what they were doing for math, and they said, "Oh, I watch Miss Lisa." So it was like, I have fans in Texas. All right, so here we go. Thermochemistry, Unit 5, and about half of this you already learned in honors. No, 3/4 of this you already learned in honors. So this is pretty easy. Where did I put my copy of the notes? Here they are. Okay, so thermodynamics, heat or energy, has to do with why a reaction does or does not, oops, put it on draw, it works better, does not occur. So this was your warm-up question. Heat or energy units are joules, usually in AP, not calories. So if you remember in honors, when I teach this, I try to use a lot of calories because I want to make it more applicable, and so therefore I do calories because everybody eats and everybody knows about calories. But in AP, we're going to use joules more. And that 1 calorie equals 4.18 joules. And it's because calories are based on water. Calorie is the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. And so 1 calorie equals 4.18 joules. So that's the conversion, but it's also the specific heat of water. That'll make more sense in a minute. So there are some laws. And the first one that we're going to talk about the first and second law of thermodynamics. And thermodynamics states that energy can't be created or destroyed. So always remember that in the rock, paper, scissors of science, laws beat theories. Laws are so true, they're math. Laws are like the math that make the universe go. Theories are true, and they are proven by thousands and thousands of experiments, but they change. So it's not the atomic law of matter, it's the atomic theory of matter, because we're going to know more about atoms in 5 years than we know now, and it'll change a little bit. There is also theory in common speech, like I have a theory that mean people hurt people, that hurt people hurt people. People are mean because they're hurt deep down inside. So you should be kind to mean people because deep down inside they're just hurt. So that's my mean people theory. Is it scientific? No, it's based on a little bit of observation, but have I done experiments to prove this? No. So in science, the one thing that's a little bit confusing, that confuses kids, is we have a couple of things that we call theories that are not scientific theories. Scientific theories have experiments done on them that prove them, but the theory of evolution and the theory of Big Bang does not have current experiments to prove it. That you can't, the only way to prove it would be to get a time machine and go back and see what happened. So those words are common speech theories. We have not done lots of experiments making things evolve. We haven't taken some molecules and done some experiments on them and got a man out of them, have we? We haven't done experiments and gotten a cell. And even if we did, that would be how these molecules made a man. It wouldn't be the molecules that made you, because that was in the past, and we can't go back in time and do experiments on the past. Does that make sense to you? So that confuses kids because they think that scientific theories aren't necessarily true, because you say, I've got a theory about that, and it might be true or it might be false. But the atomic theory of matter, I can assure you, is true, because it's a scientific theory, not a common speech theory. But just know what really applies here is the rock, paper, scissors of science is laws beat everybody. They're math. Okay, so we're going to talk about 2 of them. Thermochemistry deals with how energy is transferred in chemical reactions. So that's what we're doing. And what we have to do first is just do some definitions. So this is a thing that has to do with physics and chemistry. We want to limit the scope of what we're looking at so we can limit the math. If any of y'all have already had honors physics, you know that you don't consider every variable in the whole universe while you're looking at a certain experiment. You limit it to the system you're looking at and the things you're looking at, the math. Okay, so like if I do the speed of me walking across the floor, I would limit it to the where I start and where I end and the time. I would not take into consideration that the earth is turning, adding to my speed. And I wouldn't take into consideration that the earth is going around the sun, adding to my speed. And I would not take into account that our solar system is going around the Milky Way galaxy, adding to my speed. And I would not think about that our Milky Way galaxy is in a galaxy moving around as a galaxy cluster. I'm really zipping along right now. But when we do physics, we don't want to think about any of that math. We just look at the system, right? So we do that in chemistry too. When we talk about energy in chemistry, we're not talking about the energy of the whole universe. We're just going to talk about the energy of the reaction we're doing. And if you've had physics, you've heard this talk before, right? That we can't look at everything. That's too big. We got to narrow it down. So in chemistry, a system refers to the specific part of a reaction or process that's being studied. Surroundings is everything else that we don't care about. Everything else outside that system, including the container, air, beaker, and this is a tough one, the water. The water in an aqueous solution is considered surroundings, and we don't worry about that a lot of times. That's why we have our net ionic equations. We're not worrying about that water, are we? We're just going to look at the ions and what they're doing and the environment around it. Energy can be converted by breaking and forming bonds, changing from chemical potential energy to mechanical energy, and we've seen it in lab. We've burned things and converted to light energy. We've heard crackling and had sound energy. So we have seen some of these energy changes. Something else we have to define is work. So work in physics is using a force to move something a distance. So a lot of times we use work for things that aren't that. So I used to teach regular physics, and I showed a video in Cobb County, and there was a video with a little R2D2 looking robot who's sweeping the floor, and he's complaining, going, work, 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 because he is moving something a distance. He's using a force to move the dust a distance. But Winnie the Pooh is thinking. And he's saying, think, think, think. But thinking is not work because you're not using a force to move something a distance. So homework is not work except when you move your pencil or type on your keyboard. Then you're using a force to move something a distance. So we talk about work and energy and heat in chemistry. So heat is Q, thermal energy, lowercase q, and we're going to talk about the symbols in a second. If Q is positive, the system gains heat, heat goes in. If Q is negative, the system loses heat, heat is out. And that makes sense to me because we've already learned that in reactions, if the heat is negative, it's exothermic. Remember how we've already talked about that? Okay, so work also has positive and negative. Work is positive if work is done on a system. Work is negative if work is done by a system. So overall, we can calculate the total internal energy. Oh, before we do, I wanted to point this out. Which one do you think has more heat energy? Lake Allatoona, right close to us, or a teacup of boiling hot water? Which one has more heat? Yes. Lake Allatoona. Why?
Because it has more surface area.
It's got more stuff in it, right? If we were to take all the bonds of all the chemicals in Lake Allatoona and break them, it would release a tremendous amount of energy. If we could turn them all into a bomb. I want to say this more correctly. It would make a lot. It would give off a lot of energy. but the temperature is higher in the little cup. So the point I want you to know is that temperature and heat are two different things. Before we start talking about it, I want you to get that in your head. Heat is this total internal potential and kinetic energy. It's all the energy that's going on. Okay, so we can also look at the total energy, look at heat and work. That the change in heat is Q plus W. While we do these notes, I would like you to get out your AP Chemistry reference sheet that you will be allowed to have on the test and look at the formulas and see what's there and kind of put it in your head. Oh yeah, this formula's here. I don't need to memorize it. I do need to memorize something else. So as you go through, and the symbolism might be different. Sometimes for heat they use a Q, lowercase q, sometimes they use an uppercase Q, sometimes they use an uppercase H, but it's the same formulas usually. So just take a look. Technically there's slight differences in these, but sometimes you will see the formulas written differently. When I taught physics, they did not use the Q's at all. They only used H. I used to use an old chemistry book that never used H, only used lowercase q's for all this. So y'all have heard already that there are some symbols that are disputed. There are symbols that change. There were some symbols that were one thing when I was in high school, and now they've changed. Okay, so here's our example problem. A gas absorbs 500 joules of heat, so it's plus 500, while Q equals plus 500, while expanding and doing 200 joules of work. So work is negative 200. Calculate the change in internal energy, delta E, of the system. E equals Q minus W, that's our formula. We just plug our numbers in, and 500 minus 200, I can do that one in my head. It's 300 joules, and it's positive. So the only thing tricky about these problems is understanding when it's going to be positive and when it's going to be negative. Okay, so here's another one. A gas releases 100 joules of heat, so it's minus 100 joules, while expanding, and 70 joules of work is done on the system, so plus 70 joules. Calculate the change in internal energy of the system. E equals Q minus W. Negative 100 minus 70 is negative 30. So these can be negative. Okay, that doesn't look too hard, does it? Simple formula, simple math. So next is enthalpy. Enthalpy is the total energy of a system. In chemistry, it's the type of heat involved in breaking and forming chemical bonds. So that's going to be the answer to what drives chemical reactions. It's going to be enthalpy and entropy that we're going to talk about later. So the change in enthalpy is shown as delta H, refers to the amount of heat energy absorbed or released by a system during a chemical reaction. Y'all know RXN is the abbreviation for reaction. Heat is released when a bond is formed. So is that going to be endothermic or exothermic? Y'all think this is endo or exo that goes in this blank? No guesses? What do you think?
Exo.
He says it's exo. So the key word here is released. And when heat is released, Joseph is exactly right. It is exo. Yay! Heat is absorbed when a bond is broken. That's endo. So y'all know I'm on the Facebook AP Chemistry Teachers group, and they said that this idea is what gives kids a hard time with this concept. So we're going to do a little hands-on thing to try to put this in your brain, and I promise I'll go back in front of the camera and clue in the people who are watching. So take a stir stick and take one and pass it. Mason, take one and pass it. Everybody get your stir stick. Okay, so this is going to put it in our brains that what we're doing here. We have a stir stick. Almost everybody has a stir stick. These are Malwood. Stir stick. Okay? We're going to break it. To break it, is it going to give us energy, or are we going to take our energy and put into it? We ate some Cheerios this morning. We got some food to give us some energy. We're going to take that mighty energy and break our sticks. As we do, we're thinking this is a bond, and to break a bond, it takes energy. Okay? So, when heat is absorbed, when a bond is broken. Did you see how this stick absorbed that energy and broke it? Can you put that in your brain? Break it. Try use that little hand motion to help you remember, because this is the thing that all the AP chemistry teacher says this is what confuses kids. And they said to do this, so that's why we're doing it. I read it right off of Facebook. It said, get them to break something and make them think it takes energy. Energy has to be absorbed to break it. Okay? Got it? All right. It's all in your brains now. 6.2, energy diagrams. Temperature is different than heat. We already said that. It's how hot or cold something is. It's the average kinetic energy of the particles in degrees Celsius or degrees Kelvin. So everything's moving. In my honors, we watched a really old video from the 80s called Eureka. And we saw it was from Canada, public broadcasting, and we saw molecules doing the dance of the molecules. And they would dance faster with more kinetic energy and be hotter, and they would dance slower with less kinetic energy and be cooler. So heat and temperature are different. Temperature is the average kinetic energy of the particles. So get that in your head. Next idea, you should already know. So energy diagram, we've already seen those last unit. And it's exothermic when the products are lower than the reactants. So the reactants have a higher enthalpy, higher energy than the products in an exothermic reaction. Being exothermic is a driving force of reactions. Now, sometimes they write it fancy, but don't let the fancy writing it confuse you. If delta H is less than 0, that means it's negative. Heat is negative in exothermic reactions. Okay? Everybody understand that? So sometimes they get all fancy writing it like that. Most reactions are exothermic, by far. Next, endothermic. The products are above the reactants. The reactants have a lower enthalpy than products in endothermic. And then you can write it this way. Delta H is greater than 0. That's just fancy math for it. It's positive. These are not favored, but they do happen, and we're going to talk about them more in Unit 9. 6.3, we're rocketing along through these AP concepts. Heat is transferred from hot to cold because of kinetic energy bumping. Okay, so we know cold doesn't really exist, so we could say heat is transferred from hot to less hot, but you know. But cold, we know what that means. So heat always flows from hot to cold, from more hot to less hot. And the reason why is the molecules are bumping into each other, and as they do, they make more molecules move, and then that heat is transferred. So here I've got some hot air. See, he's all hot, he's mad. And some cold drink. Eventually, this heat energy is going to go into that cold drink until they are the same temperature. So it's going to melt that ice, it's going to warm up that drink, and eventually that drink is going to be the same temperature as the air around it. It reaches an equilibrium of temperature. Okay, next. Heat capacity and calorimetry. So, specific heat, I didn't leave something off, dude. Nope, I said that. Okay. Specific heat, do y'all remember learning about this in honors? Is a physical property of a substance, you look it up in tables, that is the amount of energy needed to change the temperature of 1 gram of substance 1 degree Celsius. What, do y'all remember the symbol for specific heat? It's a C, a lowercase c. What is that? What have we also learned that as a symbol for? Speed of light. Okay, so this is another one of my soapboxes. When they make me, over there's my crown, y'all can't see it in TV land. When they make me queen of math and science, I'm going to have a shocking idea. We do not need to double up symbols. There are more alphabets than English and Greek. Russians got all these letters we could use, ready to go. There's the Asian languages. They have some symbols we could use. We could have them each have their own symbol. Wouldn't that be easier than trying to use, because sometimes they'll be the same symbol that you would use in the same discipline on the same kind of problem. So it's really a bad system. They are too narrow in their idea of alphabets. There's more, we could get some ancient alphabets. Who knows? There are alphabets out there. Could be a cooperative learning project between linguists, people who study languages, and scientists. Everybody gets their own symbol. Revolutionary idea. Okay, so back to specific heat. Which cools off first if I have two things that are hot? Equal temperature to start with, water and aluminum. I give them 5 minutes to go touch them. Which one's going to cool off first, the water or the aluminum? Okay, let's try it again. I got an empty pan on the stove that's aluminum. I have another pan that is full of water. I heat them both up very, very hot. I turn them off. In 5 minutes, I've set them both off the stove. 5 minutes, I go to touch them both. One's hot, one's cold. Which one is the hot one? Yes. The water is hot. You do not want to put your hand in water that was boiling 5 minutes ago. You will be burned. You're going to urgent care at that point. Which one cools off first? Aluminum. And why is that? Because water has a high specific heat and aluminum has a low specific heat. Well, that's not really an answer. Why does water have a specific heat? Well, it's because it's shaped like that. It's negative oxygen, it's positive hydrogens, and it's polar. And those positive and negative stick to each other really hard, and it sticks to itself, and it resists change. It's inertia. It does not want to change. It takes a long time to heat up, and once it heats up, it doesn't want to cool off. It wants to stay hot. And you know, we wouldn't have life on our planet without that property of water. We are the water planet. There's no other planet that's been found like ours, covered in water. We're covered in water. They say now that there's 2 to 3 times as much water inside the earth as the ocean. Isn't that crazy? We're made out of water. That water's in the air. It's in the clouds. We have the hydrologic cycle. Remember that from, what was that, 6th grade? Was that hydrologic cycle? I thought 6th grade was earth science. You should have learned that then. So if it wasn't like that, if water didn't have its high specific heat, then we would be like all other planets, and during the day we'd be too hot for life, and at night would be too cold for life. But during the day, all that extra energy that would burn us to death gets absorbed by our oceans. And then at night, it's released very slowly by the oceans, and it keeps us warm. So it's like we have this little solar heater. Then in the day, it gets charged up, and at night, it releases. But it's also a solar cooler. So I guess it's a heat pump, because it can do both. So if it wasn't for that, we would not have life on this planet. So like if we go to Mars and colonize it, that's going to be one of the problems, is temperature regulation, because Mars is not the water planet, it's the dusty red planet, right? Okay, let's move on to page 4. We're rocketing along. So water sticks to itself, and that's why it's got that property. So enthalpy is heat. And one of the things we have to know is the change in heat formula, which I call the MCAT formula. Look on your AP sheet and make sure it's given to you. Could be a lowercase q, could be an H, could be an uppercase Q. But I think they give you that formula, don't they? Okay, so I usually, and I can't believe I forgot it, put a little kitty cat in my notes right here. I'll have to go back and add a kitty cat to the master notes, because I think it sounds like you're saying cat, like a kitty cat. but it's heat equals mass times specific heat times change in temperature. But doesn't that look like cat? So we can have the little kitty cat going, maybe he's eating a fish. There we go. That's a much better picture. Okay, so what does M stand for? It always stands for this. It's pretty consistent with this one. It's mass in grams. C, we already said, is specific heat. T is temperature. That's pretty consistent. T is temperature. And triangle is change or difference. But here it means change, the change in temperature. We'll say or difference. Okay. So here's the example problem. You drink 1,000 grams of ice water at 0 degrees Celsius. So we have a mass, we have a temperature, and we have another temperature. And what we want to know is what is delta Q. That's our question word. And we know that it's water. So we are going to memorize, or maybe they'll give it to you, but I think you should memorize it, that the specific heat of water is 4.18. Okay? Because that's just sort of expected for you to know, like how water boils at 100 and freezes at 0. These are things that you just know, okay? So we write our equation, we substitute in, we multiply, and we get 15,466 joules. That's our change in heat, our change in energy. So where we get our energy is from food. That gives us our kinetic energy. That keeps us alive. Yes?
Do you know why we don't change to Kelvin? And why do we stay in Celsius?
We stay Celsius for everything but the gas laws. Gas, if it's a gas, it's got to be in Kelvin, because the math doesn't work if you have negative numbers, but heat works with negative numbers. That's why. Good question. Sometimes you are given or asked for molar heat capacity instead of specific heat. It's a simple gram to mole conversion where you use molar mass. So sometimes they try to be tricky. You'll see different problems in your practice problems. But it's just a simple, oh, I've got grams, I need to change it to moles. I use molar mass. Okay, so here's another example problem. A 50-gram piece of aluminum, let me give you a little background on this first, take you in the Wayback Machine. Do you remember when we did a lab in honors, and I'm pretty sure Miss Corden's class did too, where we used these little pink styrofoam things, and we heated up metal, and then we poured it into the water in the little pink styrofoam thing, and we took the temperature of everything. Remember that? And in my class, it was a mystery metal, and they had to solve for specific heat and figure out what the metal was. Do y'all remember that? Okay, so this is a very typical problem where you are doing that. And so here in this problem, we have heat that is in the aluminum and it goes to the water. Well, it's the same heat. The heat lost by the aluminum is the heat gained by the water. So you can set these two, Q equals cap, together, equal to each other. You will be given all the variables but one, and you solve for the one you don't know. So when we did it, what we solved was for the specific heat of the metal, because we didn't know what metal we had. And we used that to identify the metal. In this problem, the thing they don't have is final temperature. They knew they had aluminum. They measured everything else. They put it into the equation, and they solved for temperature final of aluminum. So what I would do if I was doing this is I would make that an X, because that looks more like regular algebra to me, and I know how to gather up my terms and solve for X. Okay, so I'm trying to figure out what lab we're going to do for this unit. And since we already did that other one, I thought maybe we'd do this one where we have a known metal and do it again and solve for final temperature and then measure final temperature and see if we get the same thing and we could find out our error. I don't know. That's not really exciting, is it? Heating up metal and pouring it in water and taking its temperature and getting its mass. There's mass too. I don't know. I'll look on that Facebook page I told you about and see if I can find something better. Because, I like y'all's AP labs to be a little fancier than honors and We already did this one. So anyway, that's the math here. And when I did this math, I got 74.6 degrees Celsius. Solved for that x. All right. Everybody remember how to do that? I told you a lot of this was review. A lot of this you already know, and hopefully you remember this. What is the device used to measure heat change? It's a calorimeter. It looks like a calorie meter. Calorimeter, or calorie meter. So there are different kinds. There's one called a bomb calorimeter. That sounds more fun than it is, where you've got like something electrical to heat it up and burn it and see how much heat it gives off. Of course, we have this kind, a styrofoam cup. Now, when I taught in Cobb County, it was actually a styrofoam cup I bought at Kroger. But at here, we have those little pink ones are actually a little better. Our math turns out better than it did in Cobb County. It's like the one piece of equipment we have better than Cobb. Pink little styrofoam cups. That came from a science supplier. All right, so y'all remember that. 6.5, energy of phase change. And hopefully you remember this from honors. It takes energy to go from phase change to melt or to boil. And so this is a heating curve, heat, energy, and temperature. And we'll pretend it's water. While it's ice and you heat it up, its temperature goes up. But once it starts melting, all the energy goes into melting the ice and its temperature doesn't change. And then once all the ice is melted, then the temperature will start making the liquid temperature go up until it gets to vaporization, to boiling. And then the boiling water stays the same till all the water is gone, and then it becomes a gas, and the temperature can go up. So melting and vaporization, look, this must be British. They spelled vapor with an O-U. Okay, and there's, so temperature does not change while phase change is happening. It is called latent heat, and temperature does change when it's not in phase change. That's called sensible heat. But I think those terms, latent and sensible, are more common in physics than chemistry. So you might not need to know those words. Next, calculate the amount of heat required to melt 50 grams of ice at 0 degrees, given that the enthalpy of fusion of water is 334 joules per gram. So all you have to do is multiply 50 times 334 joules per gram. Grams mark off. And I got 16700, 16,700. That's not too hard to do either, is it? We're going to do great on this unit. 6.6, introduction to enthalpy of reaction. So we've already learned this. If it is endothermic, is heat positive or negative? It's positive. Exothermic is negative. So sometimes they will write heat as positive in the products or reactants, and you just know if it's written in the reactants, it's endothermic. If it's in the products, it's exothermic. Sometimes they'll tell you the heat separate from the reaction, and if it's positive, it's endothermic, it's a reactant, and if it's negative, it's exothermic, it's a product. Okay, so little star there, you have to know that. Heat can be treated like other components of a reaction with stoichiometry. Okay, so I have a little question here. Here I have a formation of a gas in a reaction. Do you think this reaction is endothermic or exothermic? What's it on? It's on a hot plate, so what does it need? Energy, so is it endo or exo? It's endo. Endo. So a lot of the questions in this unit is, you have to kind of think about it a second. That's why I gave you the sticks to break. So this would be endothermic, because I'm having to, for some reason, I'm having to add heat to this reaction to make it go. Okay, the combustion of methane, CH4, releases a certain amount of heat per mole of methane reacted. So if it releases it, we know that it's exothermic, it's in the products. How much heat will be produced when 10 grams, that's what I know, of methane is completely burned in excess oxygen. That means oxygen is not important. So I do this like a regular stoichiometry problem. And I know some of y'all didn't have me for honors, but this is the method I think is the best way to do stoichiometry. First, write down your equation and make sure it's balanced, and use it as a table to fill out all your information. So I always write down what I know, 10 grams under the chemical it goes with. I have 10 grams of methane. And then I put a question mark under what I don't know, which is how much heat. The next line is determined by this line. If this line is grams, you put the molar mass, because what goes with delicious graham crackers is M&Ms. That's why there's M&Ms on my periodic table. If what is on this line is liters, what goes on the next line is 22.4. If what is on this line is molecules or particles or atoms, what goes on this line is 6.02 times 10 to the 23rd power, Avogadro's number. If what is on this line is moles, you put nothing on the next line. If what is on this line is heat, you put on this line the heat given in the problem. Okay? We can add that one little fact, can't we? The third line is the mole ratio that comes from the balanced chemical equation. This is an understood one, so it's 1 on this side, and on the side with heat, it's always 1. This amount of heat is per 1 mole. Then what do I do next in a stoichiometry problem once I have my facts? I'm going to draw my U. So I put a dot with what I'm given, and I draw a arrow around to what I'm trying to figure out, and that tells me the order to write down my variables in my train tracks. This arrow can go this way. It can also go that way. If it's endothermic, right? Or any stoichiometry problem, it can stay on one side. It can go from reactant to reactant. It can go from product to product. And I had a question about that on the last test. Somebody asked me, is it allowed for it to stay on the same side? Yes, it is. And that's why I get you to draw the U, because that confuses kids. Draw a line from what you know to what you don't know. Any questions so far? Okay, so now what goes next in our problem? We write what we know. And so we start right here. We had 10 grams of methane. Now we draw train tracks on whatever this unit is. We push it into the denominator, and it's more fun with sound effects. So push grams to the denominator. You go around the U to see what number goes with your unit. And the number is 16. Does everybody see how I got that? And what's on the other side of the fraction bar? Well, right there's the fraction bar, and what's on the other side is mole. 1 mole. There's an understood 1 with that mole. Now I push 1 mole to the denominator. Just the mole, not the 1. I go around the U to see what number goes with it. It's 1. Now, when kids mess up stoichiometry, this is where they mess it up. They will flip their mole ratio. The moles of what you know always go in the denominator. The moles of what you're looking for go in the numerator. So the arrow tells you, you come to these moles first. You always fill out your denominator first, except for when you start. And then it goes in the bottom right there. Now what's on the other side of the fraction bar? A colon in math is a fraction bar. So what's on the other side is 1 mole of our heat. The mole goes to the denominator. What number goes with it? Well, it's that mole right there. It's a 1. What's on the other side of the fraction bar? Negative 890 kilojoules. Grams cancel out, moles cancel out, moles cancel out, and I'm left with what I wanted, kilojoules of heat, and I got, no, there it is, negative 555. So everybody remember stoichiometry? You can do this. Heat being a different variable is hard. I should put it on my box up there too. We'll put heat on the bottom with a cute little mole. He can be holding heat, put your given heat in there. All right, sometimes they just give you the heat, and you need to realize negative is exothermic, a product of the reaction. So sometimes they'll say it's like a product, and you have to know to make it negative, to be tricky. Sometimes it's a multi-step problem where you have to use Q equals MC delta T first to solve with the moles, or use density or molarity. We'll see some examples in the videos. So Krug, we're gonna watch his video for 6.6 A and B in class, because I want you to see some of these, where they can throw something that you have to solve before you get to what you really want to do, problems. And I think he's got some good ones. If a reaction is reversed, sometimes they'll say, this is the reaction, this is the heat, but we're gonna reverse it. All you do is you change the sign of delta H. So that's like another little trick they can throw at you, is reversing the reaction, and you just got to know to change the sign. Okay, how are we feeling? Hanging in there? Okay, here's an example. Calculate the amount of heat energy needed to be absorbed by the system, it's absorbed, when 25 grams of ammonium nitrate dissolved completely in water, given that the endothermic reaction, so they told us it was endothermic, they're being nice, and they told us it was plus 25, and we can see it here that it is a reactant, we see it's 25 over on the reactant side. So we're given we have 25, we're looking for the change in heat. This is grams, so we write the molar mass. That is our given heat, which is what goes in that line, and our mole ratio is 1 to 1. 1 to 1. So our U, we're going to go from here around to there, and we just do the stoichiometry. I just wanted to show you an endothermic one, and I wanted to show you one where they're both on the same side of the arrow. Okay, there was my 1 to 1. He got left behind. Okay, so let's write this out. We start with what we know, 25 grams. We shove the grams in the denominator. We write the molar mass, 80.04 grams per 1 mole. Now, on the real, I'm doing this fast. On the real AP test, you put units with this. You tell what it's grams of. Don't just write grams. Do better than I'm doing. Our mole ratio is 1 to 1. We have 1 mole of our heat, and our heat is positive 25. That's kind of bad looking. Let's fix it. It makes it look like it's saying 125. I got a little crazy there. All right, 25.7 kilojoules, and there's our answer, 8.02 kilojoules. Okay, that's not too hard, is it? Very similar to what we've been doing. So Q represents heat transferred in a reaction in joules. We're talking about units. Delta H represents the enthalpy of a system, meaning total heat content, so it's usually joules per mole. And here's another sign. Sometimes delta H gets a little degree mark, like temperature. And that's a symbol meaning that this is at STP. So later we're going to see that a degree can mean at STP. We're going to see that in later units. So we can just go ahead and learn, if something has a degree that's not temperature, then it probably means STP. Once again, we're using the same symbol to mean something different. Just make me queen. All right. And you notice I want to be queen, not president. I don't want to be voted on. I want to have a benevolent dictatorship. I don't want input from my subjects. So I probably am never going to get it. But, you know, we can always hope. Okay, 6.7. Bond enthalpies. See, I'm in a unique position. As someone who knows science and education, I see what gives people problems and what can help fix them. That's why they need to make me queen. Both in science and math, I want to be queen. I'm going to rename all those properties from middle school that don't make any sense. Instead of calling it, commutative property, we're going to make them actually sound what they mean. See, we can fix it all. Okay. 6.7 bond enthalpies. We're going to learn 4 ways to calculate delta H. This is way number 2. Sometimes you calculate it from bonds broken minus bonds formed. that little Greek symbol is the summation symbol, and it just means add things up. And I heard from first period that y'all had not learned that in math yet. I teach it at the end of Algebra 2 when I've taught math, but I think y'all don't learn it maybe till pre-calculus. So anyway, that just means add things up. It's fancy, I like it. Okay, so here's an example problem. This is a classic example problem using bond enthalpies to calculate enthalpy change of methane combustion. So this is burning methane, and notice it goes one way. You can't get the methane back usually. List the bonds broken and the bonds formed. They will give you numbers on the chart. So here's our given. This is the energy in each type of these bonds. And then you look at it and you count up how many bonds are we going to have to break? If you look at our methane, it's 1 carbon attached to 4 hydrogens. That is 4 carbon-hydrogen bonds that are going to get broken. So we take this carbon-hydrogen and we multiply it times 4. If we look at our oxygens, oxygen is bonded to itself at a double bond, and then we got 2 of them. So we look at this oxygen double bond, and we multiply it times 2, and we add them up. That's what the summation symbol means. So step 1, identify the bonds that are broken and how many of them you got, and then multiply them and add them up. And then you do the same thing with the bonds that are formed. You're forming, in water, you form 2, each water has 2 OH bonds, but we had 2 of them. So 2 times 2 is 4, so there were 4 OH bonds, and carbon oxygen, carbon dioxide, if you remember, it's got a carbon in the middle and it's double bonded to 2 oxygens. So carbon dioxide has 2 double bonds to oxygen. We built that in a lab where we made models. But anyway, and there were 2 of them, so we multiplied 2 times 799, add them up. And then you just subtract the bonds broken minus the bonds formed. And I think they give you that formula on your AP sheet. Yes? Don't even have to memorize it. You just subtract, and let's see what I got. I got negative 824, which means it's exothermic. Sometimes you're given, which makes sense, burning methane would be exothermic. Sometimes you're given the total and everything but 1 bond, and you have to solve for it. Just put it in the formula. 6.8. Enthalpy of formation. A third way to calculate for change in heat of a reaction, enthalpy of formation. So delta H sub F, or sometimes it's delta H with the little degree mark, is the change in enthalpy when 1 mole of the compound forms from the elements that make it up. So like you want to know how much energy it takes to make 1 mole of this stuff. Now notice there are weird fractions in our reactants but not in our products. Everybody see that? Okay. The reason why is if I had written this reaction normal and balanced it, there would not have been the coefficient of 1 for these products. But we only want to know it for one mole. So we have to we have to divide by whatever the coefficient would be. And that makes weird, and what you do to one side in math, you have to do to the other. So that makes weird fractions over here. Did you follow my weird fraction explanation? Okay, because we want to know the heat made for just one. So negative means exothermic here. The weird fractions come from making just 1 mole. And so it's like a recipe, and we're only making 1 batch. We have to adjust our recipe, so we're only making 1. We're not bringing extras to the neighbors. Okay, so here's the formula for that. It's the heat of formation of the products minus heat of formation of the reactants. So here is how you do the problem. They're going to give you an equation, and then they're going to give you the numbers for these heat of formations, and then they're going to, or else you'll look them up on a table. Okay, so we can look at our products here and see how much what these heat of formations are. Now notice We have a heat of formation for carbon dioxide and water and methane, but we don't have one for oxygen, and this is why. Oxygen is a pure element. It's only made out of one kind of chemical, where the rest are made out of more than one chemical compound element. So we consider oxygen having been formed at creation, and we're not looking at elements were formed at creation, so their heat of formation is 0. We're not calculating creation. That's too far back for us. Okay? Everybody got that in your head? If it's a pure element like oxygen, we got 2 of them, but it's 2 times 0 is 0. It's an element, so nothing to form. It was already formed. Law of conservation, right? Okay, so now what we do is we just plug in our numbers into our formula, products minus reactants, and I got negative 803. It's negative, so it's exothermic. Sometimes they'll give you the total in one of the H of formations, and you solve for the other one. Okay? Last section, Hess's law. And you learned this a little bit in honors in my class. I don't know if Gordon did it or not. But we'll go a little further with it. Oops. Okay. A fourth way to calculate delta H for reaction, entropy. Does anybody remember what entropy is from honors chemistry? Yes, Maxwell.
The nature of everything to eventually just go into a form of destruction, just dip into.
Yeah, that's it. A little depressing, but yeah. So he said everything's going to eventually just go to chaos and destruction. So not to put a damper on your day, but entropy is a law. So it's a law. It is also called the second law of thermodynamics, and it is a measure of the degree of disorder. And what it says, this energy, that order always goes, or entropy always goes from more order to less order unless acted upon by an outside force. So it's the degree of disorder. And the example chemistry books always use is your room. That your room is messy, Mary Poppins is not true, a spoonful of sugar and the room is not going to clean itself. You're going to have to get in there being the outside force and clean it. But in a way, that I don't like that example is good because you actually used the energy to make it. It didn't disorder itself. Let's be honest. You messed it up, right? Okay, or maybe your mom tossing your laundry in there or something. Okay, so I like this one better. I love Six Flags. Okay, but I love it for what it is and what it's not, okay? Six Flags is not Disney. I love Disney more, but it's too expensive. I love Six Flags, it's local, it's close, and I can easily afford a season pass if I buy it on special. The best special of the year is always on Labor Day. So you can put it on your calendar, save your $55 and get your season pass. Usually a season pass is less that day than a one-day admission with no discount. So I love Six Flags. It's been around as long as me. It's old. And when I was young and they first built it, they tried to be like Disney and Imagineer it. You might not have ever realized that, Six Flags, but they tried to Imagineer. And in particular, they wanted it to reflect Georgia history. So the section where the Dahlonega Gold Mine little roller coaster was to reflect that the first gold rush in America was in Georgia, in Dahlonega. The first gold discovered was here right where we are in Paulding County and Villa Rica. And the very first thing people started gold mining in Villa Rica, they didn't mine it, they just panned for gold. And actually, there's a museum there, the Villa Rica Gold Museum. And you might have been on a field trip, but the money they got to start Coca-Cola was gold panning for gold in Villa Rica. Then in Dahlonega, Georgia, up in the mountains, somebody had a gold nugget they thought was just a rock, and they were using it as a doorstop to keep their door from going back and forth. And then somebody realized it was a giant giant gold nugget worth a fortune, and they started the Dahlonega gold rush, and it was the first one, but it wasn't that big, and they kind of got tired of people destroying the mountains, so they were like, we're going to stop this. And then the one started in California, the Miner 49er, but ours was first. So the Dahlonega gold mine is originally was supposed to be a runaway mine train in Dahlonega. Have y'all ever realized that? And it had little covered wagons on it that had little barrels of explosive for dynamite because they blasted the mountains. They also used water to blast the mountains to get the gold out. And they were these cute little covered wagons, and they had little barrels on them, and it was all themed. Well, nobody kept this up. Those little covered wagons, throughout my life, I've seen them have entropy happen to them. The canopies got torn off. Then the wood rotted. And now, to this day, I went at Christmas, I went to festival, holiday in the park, and that chassis is still laying out there rusting since I was a little kid. They are just letting entropy happen. And this is a chemical process that no one went out there and destroyed that, like you might have destroyed your room. It is just chemical processes have happened, rust has happened, decay has happened, and entropy has happened. I still love Six Flags. But let's be honest, if this was Disney, they would have kept that cute little wagon up, and this ride would have dumped you into a gift store, and you could have bought a plushie of the wagon and probably a pin. Maybe a lollipop shaped like this. You'd have this wagon on a t-shirt. Six Flags just lets it lay out there and rot. So next time you go to Six Flags, I encourage you to go. I love it. I've already got my season pass for 2025. But in the summer, you go to Whitewater. It's too hot. Spring and fall, winter, Six Flags, summer, Whitewater. When you go, ride the Dahlonega at least one time and look for the chassis that are just laying out there rotting. I will be very shocked if they cleaned them up since Christmas, because they were there at Christmas. So anyway, there's my entropy. Unless acted upon by an outside force, things go from order to disorder. So that's another one that we have talked about before when we were talking about laws and theories, and about how laws beat theories, but theories are true in science, but in common speech they might not be. Okay? Laws are so true they're math, they're what govern the universe. Theories in science are true, like the atomic theory of matter. Things are made out of atoms. We saw one in a video, a little blue one just floating there. But the thing is we will know more about atoms in 5 years than we know now. So theories in science change. Laws are math, and they pretty much stay the same. We got these laws that are these math equations, and they stay the same. Entropy is a law. So with rock, paper, scissors, laws beat theories. But there's also common speech of theory, which is not necessarily true. You could have a theory on something and it not be true. So one of the problems with one of our common speech theories is evolution and Big Bang. Evolution and Big Bang both violate entropy. Do you understand this? The theory of Big Bang is you start with a softball size of matter, it explodes, and you get planets, solar system, galaxies, comets, all the great stuff. Evolution, you start with primordial muck. Atoms get together into molecules, molecules get together into biomolecules, biomolecules get together into cells, cells start dividing and get together to be something else, and eventually you. Do you see how this is order from disorder, and according to our theory, not acted upon by an outside force? So there's a problem with it. It violates entropy, and you kind of in your gut know that there's something more we got to learn about this, because the way we've got it right now is incomplete. Because if we had an explosion in a gold mine, would gold watches start flying out? Your gut kind of knows entropy and knows that's not happened. That you can't get something that order from that disorder. If we had Rolex watches come out of it, there's no way. And you are so much more complex than a watch. So what we are saying with those two theories is more unbelievable than the gold watches, because you are more complicated than a watch. We know everything about a Rolex. We can take it apart, we can put it together, we can fix it. We know everything about it. We do not know everything about you. My son Nathan right now is doing research at Georgia Tech, trying to figure out what copper does in unborn babies, and they don't know. Too complicated. There's things we don't know. We're discovering things all the time in medicine, aren't we? And about the body. They just found a whole new organ system recently. It would collapse, so nobody was seeing it. But now we know about it. It's how they think cancer spreads through the body. So anyway, so just keep these things in mind. What's a theory? What's a law? What's common speech? And what is entropy? So entropy always goes from more order to less and less acted upon by outside force. Now, this was our warm-up. Enthalpy and entropy are what drive chemical reactions. Okay? It does not matter if this is in steps or all at once, and that is Hess's law. So it doesn't matter if you do a reaction in steps, like how we learned last unit, or if you do it all at once, the energy still works. You can add up the steps and get the total. Hess figured out that. So here's an example. We have reaction 1, reaction 2, and we get the overall. And we learned last time you add them up and you mark out things that are on both sides. So I can mark out those. So I could add those two together. Everybody remember that from last unit? And then I can also add up the heat. So I would take the heat of X plus the heat of Y makes the heat of XY. Anyway, y'all don't need to be discouraged about entropy. We're going to figure it out. We're going to figure it, there's still things to learn. Aren't you glad? Y'all are all super smart. Y'all can be scientists. Y'all can do research. You can figure these things out. And the complete heat death of the universe is a very long way off. It'll be fine. I don't know if we'll figure that one out, but it's a long way off. This universe has a lot of heat left in it for now. Okay, so here's an example problem. Diamonds and graphites are allotropes. That means they're the same chemical arranged with different bonds. So carbon, it is in two forms here. You can burn a diamond and turn it into graphite. We saw that in honors in a video with Julia Childs, burnt that diamond. Or you can add energy to graphite to make a diamond. You can turn your pencil into a diamond. How much? The enthalpies of graphite is this, and diamond is that. So you have to do it in steps. So you take the graphite and you add oxygen and you get carbon dioxide, and that much heat is changed. And then you take the carbon dioxide and you get diamond and oxygen, and that much heat is changed. You mark out the things, the intermediate and the catalyst. You add them together and you can go from graphite to diamond. You add these up and the answer is, the difference is 2 kilojoules. Usually though, that's sort of like an honors level problem. Usually in AP, you have to manipulate the two reactions to get the third reaction. So what you do to one side of an equation, you do to the other. So if I had to multiply an equation to get this stuff to mark out, okay, that's what we're trying to do. If you multiply, you have to also multiply by the heat. The heat gets multiplied too. So when you put your parentheses outside of it to multiply distributive property, one of those properties, I might keep that one, but it'll be up for debate. Distributive property, you put your parentheses and multiply it times everything on the inside. Don't forget that the heat gets multiplied too, okay? So, and then sometimes you have to reverse them. So here's an example. Calculate the enthalpy change of the following reaction using Hess's law. And that's just about specific heat. Metals have low specific heat. There are medium specific heat things. Water is always a high specific heat. That might be water. It might be high. We all know what's in that cup. Okay, calculate the enthalpy change in the direction of carbon with oxygen to form carbon monoxide gas. So there's a two-step problem. We have the heat, and we want to add them up and figure out what the heat is. But before, we can't just add these up. We have to see what's going on. And we notice that there's carbon dioxide here, but there's no carbon dioxide in our overall equation. So we're going to need to flip this equation. We're going to write it the other way. And when we do, we have to change the sign of heat. If you flip a reaction, you change the sign. And then we'll have carbon dioxide on both sides, and we can mark it out. So here it is. We flipped it. Now I can mark those out. But notice what's going on with my oxygen. In my products, I have no oxygen. But right here, in my oxygen, I have a half of O2. And in my reactants, I have a whole O2, and I'm supposed to have a half. So remember in math, when you have x and y squared and y, and I want to cancel out my y's, I'm allowed to cancel out this one and cancel out just one of those. Remember that in algebra? Okay, so that's what I'm going to do here. I want to cancel out all of that, half of what O2, and here's a 1, and I can divide that 1 into 2 halves and cancel out one of them, and I'm left with a half of O2. Can you follow how I did that? Okay, so now I've got my half of O2 here, then I add them up, I change that sign, and I got the answer. Sometimes you must multiply the whole equation and the H to get things canceled out. Ta-da! Unit 6. This is easier than Unit 5, isn't it? I see my kids are nodding yes. Science is great.